Okay, YouTube, in my last few videos, we've looked at solving polynomial inequalities. In this video, we're going to look at how to solve a rational function inequality. And in the last three videos, what's been really helpful is to look at a sketch of the graph of the function to determine what are all of the x values for which our y values happen to be less than or equal to 0, or greater than or equal to 0, maybe less than or greater than 0, but not or equal to. But basically, when you look at this graph here, we can see clearly where our function is above the x-axis and where our function is below the x-axis. What we're looking for are the x values that when you plug them in cause our y values to be either positive or negative. So one thing we've noticed in the past is that our function can only go from being negative y values to positive y values at a 0, okay? And this is a 0, but we've also referred to this as a critical value. But another thing to consider is this. We would say that our function here also went from being positive y values to negative y values right here at this x value. And this x value right here, -2, this is a vertical asymptote. We certainly know that this is a vertical asymptote, but the thing here is this, it's also a critical value. And the reason why is because we say critical values are any values for which our function can change from having positive to negative y values or vice versa. Now I say it can, doesn't mean it has to. I could have a function that maybe goes up here and then comes back down on the other side, and it's positive y values on both sides. But the point here is we say that vertical asymptotes now are also considered to be critical values. So for this function that we see here, as a matter of fact, this function 3x plus 3 over 2x plus 4, a couple things that I want to say here. First things first, we'd say vertical asymptotes occur at zeros of the denominator. And so we would say critical values, okay, well, let's put it this way. Crit values occur at asymptotes, let's be specific here, vertical asymptotes and at zeros. And then the other thing we want to point out here is this. We say vertical asymptotes occur when the denom equals 0. And I also want to say this. Zeros occur where the numerator equals 0. So essentially, here's the deal. When we solve for critical values on a rational inequality like this, we see on the picture here that clearly it can either happen at a 0 or a vertical asymptote. All I'm listing here is essentially that if you want to find the vertical asymptotes of a rational function, certainly what you do is you set the bottom equal to 0. Just really quickly checking this, we get 2x plus 4 equals 0, so 2x is -4. I want everybody to see at -2, we would have a vertical asymptote. So that's a critical value. And then setting the top equal to 0 here, 3x plus 3 equals 0. We get 3x equals -3 and x equals -1. And this right here is an x-intercept. I know this because that's what we also call this a 0. But because when you set this whole thing equal to 0, the only way that happens is if the top of the fraction equals, you guessed it, 0. So we say at -1, look at this, we say -1, we have a 0. So when we solve rational inequalities like this one, let's go ahead and take a look at this one that I have listed on the next page. We're going to tear this apart. We say let's find the critical values. You notice this has changed a little bit here. I said this can happen at zeros or at asymptotes. So in order to find these, what we're going to do is, well, first of all, we need to get the right side equal to 0. So we would get this. And we have a little bit of simplifying to do in this problem here. And this would be -1 greater than or equal to 0. And so one note that I want to make here is this. Must be a single rational expression. And so what I mean by this essentially is this. We're going to have to find a common denominator here, which I know this is over 1. So our common denominator is x plus 1. So really I would get 2x over x plus 1. And if I take both the top and the bottom over here times x plus 1, I get x plus 1 over x plus 1. And by adding these together, everything's over x plus 1 now. I would get 2x is actually minus this. We would have to distribute the negative through here. So negative, this would be negative also. We say 2x minus x is just an x, and then I would have a -1. So here's our factored expression, or not our factored expression, but simplified expression. But let's go ahead and find the zeros at the top. So we would say zeros, asymptotes. Actually, why don't we just do this? We say, well, yeah, let's write zeros and asymptotes. And over there on the left, we can see I've already got written critical values. But basically, we're going to find our critical values here. We say x minus 1, or if the top equals 0, x equals 1. So we found one of our critical values. And if you set the bottom equal to 0, we say x equals -1. That's our asymptote right there. So we say here are two critical values. We're just going to list them up here. We say x equals plus or minus 1. So in terms of our test intervals, let's go ahead and set these up here. I could really spread this guy out this time. We say here's 1, here's 2, and here's -1, here's -2, because I said. So we get -1 and +1 are our critical values. So now what we're going to do is we're going to absolutely still test values here. -2 will test, x equals 0 is certainly one I would test, and x equals 2 is another one I would test. And so our test intervals, how about we start with x equals -2. We'll do x equals 0, and then we'll do x equals 2. So with all of these right here, we can say, looking at this inequality, we want to use this one right here. We have x minus 1. When you plug in -2, we get -2 minus 1. Over now, we get -2 plus 1 is greater than or equal to 0. In other words, we get a negative thing, like -3, over another negative thing, which indeed is a positive thing, which is greater than or equal to 0. So we would say that, yes, -2 worked. And if -2 works, what we're going to do is we're going to shade all of the x values on this interval right here. And as a matter of fact, shame on me because I didn't set up my test intervals, but we say -∞ to -1, -1 to our next critical value is 1, and then 1 to infinity. But we would say that indeed this is one of our solution intervals right here. We say testing 0. Now 0 is going to be 0 minus 1 on top over 0 plus 1, which I notice comes out to be a -1 over +1. And that's negative. So, I mean, this would be false. We would not shade this middle interval. I would cross that off of the possibilities here. And then when we plug in 2, we get 2 minus 1 over 2 plus 1 greater than or equal to 0. So in this case, we get 1 over 1 is greater than or equal to 0, which is so true. And we're going to shade this way. I actually changed my colors here. So that's in the solution interval right here. So now here's the oddest thing about it. We said greater than or equal to. And so the funny thing about this is, if this function equals 0, then you're going to get 0 is greater than or equal to 0. So because this is greater than or equal to, we have to include any x values that were in this zeros category. So when I write my solution interval here, I notice that the 0, 1 does cause my function equal a y value of 0. So that interval right there, we're going to write from 1 out to infinity, and we're going to include. This. The funny story here is that from -infinity on this first solution interval up to -1, we're not going to include the -1. And the reason why, we'll write a note here, don't include, is just because there's a vertical asymptote there. We shouldn't include x values where there are vertical asymptotes, because what we're assessing is where our y values are greater than or equal to 0. And it is equal to 0 here. It's just equal to nothing right here. It's undefined, okay? So we would say these are the solution intervals right here. Cheers.